Well, what if we want to read small voltages? Whether we want to put them in the Arduino or not, we'll handle that at the end. But we want to measure a small voltage. And when I say small voltage, I'm talking about in the 0 to, say, 20 millivolt, 30 millivolt range. Because if you want to put in, if you want to read 0 to 30 millivolts, say, into an Arduino or into any computer or microcomputer, you're going to have to give it some gain. And of course, you'll probably use an op amp for that. But what I would like to propose here is a really good method and a good op amp to do that with. And one that's very accurate and has low offset voltage, which I'll explain, because of the particular part being used. And I think you'll like it. So let's start with the schematic. The schematic for it is rather simple. I'm sure a lot of you have seen op amp schematics, but would like to go over this. It's really exciting because this op amp here is the let me get it right. It's the LTC 1050, and this is the CN8 variant. And it's an IC op amp chopper stabilized 2.5 megahertz. Well, that's the bandwidth. So LTC 1050 CN8 chopper amplifier, and the chopper amplifier is a special amplifier that has internal circuitry that stabilizes the input offset voltage. And the input offset voltage is a voltage that can be very real and cause you an error on your output. So if you're going to measure very low DC signals, input offset voltage becomes very important, because if you're going to measure a 10 millivolt signal and you have a 10 millivolt offset voltage, it could cause you some problems. Well, this chip, this 1050, has a offset voltage in the microvolts, and I believe it's down into the 5 microvolts level, I believe is what it is. So you have a much more accurate DC measurement, which is what I love, measuring low DC signals. I don't know why, but I do. And this will do the job. This will measure a low DC signal and do it accurately. Now, I've got some other scribblings on the paper here that I'll explain as I built up the circuit, and I wanted to be as accurate as possible. And I'll show you why. I'll show you why I've done some calculations on there. First, let's look at the input of the schematic. I have a signal generator, and he's going to generate 0 to, say, 50 millivolts DC. He's going to throw it in through this. He's going to put it in through this 1K ohm resistor. It's going to go into the inverting input. So anything we come out of here is going to be a negative voltage. So what I did is I'm having him give us a negative DC 0 to 50 millivolts so that we have a positive output here. It just makes it easier to read and stuff for our purposes. And then the feedback resistor is 100K, and then I put a filter or integrating capacitor, whatever you want to call it here, of 4.7 microfarads, because it really stabilized the voltage when I did that. The small DC variations would really settle down when I put that there. And then I put a 10K bias current, input bias current equalization resistor here. I won't get into what that is. Basically, that's this and that in parallel. Actually, that's not true. That should have been a 1K. I made a mistake and put a 10K. That should be a 1K right there. Anyway, it doesn't matter. It works fine as it is. Let's see. Now, what I wanted to do though was be as accurate as possible. And so I actually measured the 1K resistor, and it's 997 ohms. Pretty accurate. It's a very good resistor. The 100K was actually sitting right at 99K, so right at its 1% boundary on the lower side. So 99K, 997. And I also measured the signal coming out of this, out of the signal generator. It's what its error was, and it's got a considerable error coming out. When it says 30 millivolts, it's actually putting out 27.6 millivolts, for instance. So I wanted to do a little calculation, and I'll show you the reality of what I'm looking at here. So V out was 99,000. Of course, you know that the gain of this is this divided by this times the input voltage in an inverting amplifier. So it was real easy. It's 99,000 divided by 997 times 27.8 millivolts, and that equals 22.76 volts. And that's almost exactly what it came out to be. There's other errors, but we won't talk about those. I'm just trying to get this as accurate as I can with what I have. But it's fairly accurate. So we put in 27.6 millivolts. Even though the SIGGEN says 30, it's 27.6. And we get out 2.76 volts. That's pretty good. That's a gain of 100, which is what we expect. We expect a gain of 100 with 100K and 1K here. And then our ultimate goal is to put this into an Arduino and measure it with an Arduino. And so what we want to be able to say to ourselves is we have a 0 to 50 millivolt signal, and we are measuring it with a, basically this is kind of a rough 0 to 5 volt kind of measure. 50 millivolts wouldn't show up much on an Arduino. With the amount of bits it's got measuring the A to D converter, the amount of bits it's got. So if you can convert 0 to 50 millivolts into 0 to 5 volts, you're going to do really well on inputting that into an Arduino. So let's look at what the actual circuit is. What's really going on here in reality. We had this, and I've given you some real numbers. Let's look at the measurements. First off, this wouldn't be a video without a look at the actual circuit. And we have the chip, the LTC 1050. I've got this is a decoupling. I didn't put these in the schematic. That's a decoupling capacitor from, it's powered from -5 volts to +5 volts. And so I've just decoupled the +5 volts to the -5 volts. That's all, just as good practice. The 100K resistor is back over here. I separated it out because it was just getting so crowded. My fat fingers couldn't get in there. That's the 100K feedback resistor. And what you can't see is the 1K input resistor right here. That's the 1K input resistor. I've got a signal coming in from the generator. And let's look at that. I'm just going to swing up. And we'll see if we can see it. Can we see that? That looks awfully washed out. That says 30 millivolts there at the top of the signal generator, and so that 30 millivolts is not internally measured by the signal generator. That's just what he thinks he's putting out. He's actually putting out. Yeah, I can kind of see it. He's actually putting out, when I measure him at his output. Kind of read that at an angle, that one, that meter. He's actually putting out 27. These are minus numbers because we're going into the inverting side of an operational amplifier, because I wanted a positive output voltage for the Arduino. So just, if I don't say minus, just ignore that. We have minus 27.6 millivolts that we're actually putting out of the signal generator instead of the 30 millivolts he says. Okay, and we run that through our 99,000 over 970 or 997 gain, and we run it through our actual gain that we're getting based upon our real resistors, and we get pretty close to this right here. This is our actual output voltage, 2.76, you know, blah 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 voltage. And so we're doing pretty good. We're not doing bad at all. We're putting in 27.7 millivolts, and we're getting out 2.76, 2.77, or 2.6, 2.67 volts. So we're doing pretty good there. So this is how if you want to read a small voltage, this is what you do. And you say, well, all I've got is an ordinary op amp. Well, you can use an ordinary op amp, but you will have more error to worry about. And there are some tricks to take that away. These you can order singles from TI. They're not expensive, of the LTC 1050. I think this one, it cost all of $4. And I believe I ordered 3 or 4, and I got them for like $4. And you can have you a nice chopper stabilized op amp to truly read a small voltage correctly, the way you really need to read it, and to be accurate and to be confident in what you're doing, and to measure like I've done here, to measure, you know, what is my real signal input, 27.7. What is my actual voltage output? 2.76. That's what I'm actually putting out. That's actually what I'm going to put into the Arduino. And so, so we have a reliable system here for reading a small voltage pretty accurately. And translating it into a voltage that an Arduino or any computer, any A to D converter would be happy to have, because it would be easy to convert into digitize, so that you could use it in your program. And this voltage could come from sensor, it could come from, you know, anything, Wheatstone bridge, any kind of sensor, load cell, whatever. This could be. Now, if you want to get down into the microvolts, then you have to take different precautions. Can you build up a circuit on a breadboard that's at microvolt level? You may not even be able to do that. I think I'm reaching the limit here of what you can build on the breadboard, because all of these wires that I have here, all these wires, they all introduce problems, and they all introduce some sort of error. And you start getting down in the microvolts, and you almost really need to build it up on a PCB board. Designing it is best, but at least build it up on a copper clad breadboard with the shortest wire possible, and use decoupling caps and as close as possible to the chips and all of that to really get to get the best, if you're going to go down to the microvolt level. I think I've done that a couple of times with varying degrees of success. But this one, when you get into the millivolt, seems to be a little easier because you can build it up on a breadboard and you can play with it. Okay, let's look at the LTC a little bit. Just a few. I won't bore you with everything here, but just a few of the banner specs. No external components required. They're talking about the external capacitors that are used to They're used to help with the zero offset. They're not talking about the resistors, gain resistors, of course. Maximum offset voltage 5 microvolts. That's the banners. That is the banner spec. The drift is 0.05 microvolts per degree centigrade. That's very important. Low noise from 0.1 hertz to 10 hertz is 1.6 microvolts peak to peak. That's important because that's what we're dealing with. We're in the DC range, so we're in that range. Voltage gain, low supply current, output swings to ground. That's good. And over here, it integrates on chip the 2 sample and hold capacitors usually required externally. And I've used the ones that have external capacitors, and it does take up more board space, and it's a pain, and you got to get the right kind and the right values and the right tolerance and everything. So it is nice that it's on board. It offers better combined overall DC. Okay, he's kind of extolling his virtues there. And we've already seen most of that. Now, let's see. And well, we were talking about instrumentation amplifiers in a previous video, and there's one that if you want a chopper stabilized instrumentation amplifier, you can use this along with this LTC 1043, which is another. I've not used that, but it's another chip that you can buy and use that. It goes to plus or minus 9 volts, which 18 volts total across the power supply. I was wanting to see that. There it is. Input offset voltage. This first one here. Input offset voltage 0.5 microvolts. Typical plus or minus 5. So that actually, typical is actually 0.5 microvolts. And they put in there the 5 microvolts just as a maximum, but 0.5 is pretty darn good. And I think that's it. We're not doing any frequency response kind of stuff, so what is that? Those are test circuits. I want to get down into the circuits here, into some of the example. There's a strain gauge signal conditioner with bridge, blah blah blah. There's some thermocouple. You know, this would be very low DC thermocouple kind of stuff, microvolts kind of stuff. And I have a thermocouple here, and I was going to actually play with that, but I don't have this LT1025A right here that you need. And just a few examples. Fast precision inverter, output drive, let's see, there's current sources, so all kinds of precise kind of stuff. Ultra precision voltage inverter, all kinds of precise kind of stuff. And there's a what is that? Difference instrumentation amplifier, low offset. Photodiode amplifier. There's another low signal. I was actually going to do a photodiode, but I couldn't find a photodiode. I have 2 of them, but I can't find them. And proper photodiodes, not like an LED and trying to fake it, but proper photodiodes. So anyway, that is the LTC 1050. It's a very impressive chip. And if you can pick one up for a few dollars, and Linear Technology, you can order it for a few dollars, and you can start measuring low voltages. How low can we go? Well, let's go check. Okay, let's see. We're going to do a little shadowing. You might get some shadowing in the camera here, but I've got on the LCD is the input, or rather, that's the output, the actual output of the signal generator, and then what you see on the BK Precision to the right there is the actual output of the operational amplifier. So if I reach over here and I go down to, let's go to 20, I was at 30 millivolts, which was actually 27. See, if I go to 18.1 millivolts, then we see we're at 1.81 volts DC. We're still good. That's pretty good. So let's go down to 10 millivolts, or what it says is 10. It's actually, what does that say? 8.6. That's 8.6 millivolts. And what are we putting out of our LTC 1050 is 0.867 volts. Pretty darn good. For a a few dollar chip and a few dollars worth of components, you can really get an accurate low voltage measuring device to for your circuits, for your whatever you're going to be working on. If we go down to 5 millivolts, which is actually 3.9, because the signal generator is off. 3.9 millivolts, we see 396 millivolts, because it's multiplying it by 100. We see 400, we see around 400, 398, 397. We see it's getting a little fuzzy here. It's starting to drift on us a little bit, because the signal generator is probably getting a little fuzzy. He's probably starting to waver a little bit in his output. I don't have a scope hooked to it, but you probably see some noise going up and down on that. But a 3.9 millivolts, and we're getting out 400 millivolts as our output signal. That's not too bad. And if we go down to 1, we're at 1 millivolt now, which actually is 0.2 millivolts coming out of the signal generator. And at 0.2 times 100, we get 23, 22 millivolts coming out of, so 0.1, 0.2 millivolts. 0.1, 0.2. I don't have a more accurate meter for that side of it. We're getting right around 20 millivolts output. So yeah, we're doing about as good as we can get at that level. So we're still not doing all that bad, even though we're down to the 0.2 millivolt range, 0.1, 0.2 millivolt range. We're still getting 20, 21 millivolts output. Now, well, I can't measure 21, 22 millivolts output out of my in my Arduino or whatever. Well, you could throw this into another stage, do exactly the same thing and throw it into another stage, and then you'd be fine. If you're getting down that low in input voltage. But I just thought that would be interesting. That's how you put together and read low voltages. And the reason why I'm not showing what we're going into Arduino is you put it into A0 and then you read it, and that should be that simple. But I'm having a problem when I connect grounds between the Arduino and my circuit. When I connect the grounds together to share the ground, everything goes haywire, and I've not figured it out, so I'm just going to leave that for another day. The important part of this video was to show how to how to measure that low voltage, how to measure it accurately, how to get it to a level to where an Arduino could read it, and then I'll figure out the ground thing and get back with you. But and then get it to an Arduino to where you could read it into your program and act on it. All right. Well, thank you for listening. I hope you found that fun. I did.